So we're going to go over the waves assessment. First question. Students adjusted the speed of the motor so that the bar hit the water more times each second. What happens to the frequency of the waves produced? We saw this with our core prac that with the increasing the frequency, the gap between the wavefronts will get shorter. So the first answer is the frequency increases. Second part, describe how the frequency of the water waves in the ripple tank can be measured. We did this as a part of our core prac. We took a video recording. There was a mark on the screen, and we counted how many waves passed a point in a given time. So we counted after maybe a couple of seconds how many waves passed, and then we counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How long did that take? And then we divided that by the number of seconds. So if 15 waves passed in 6 seconds, then we need to find out how many waves passed in 1 second. So we divided that 15 by 6. So here we've got the equation, the period equals 1 over frequency. We put the numbers in. The frequency is given in 5 hertz, and 1 over 5 gives us first mark, 0.2 second mark, seconds, the third mark. Here is a ray diagram of light passing through a concave lens. The image is produced on the same side as the object. This dotted line indicates that the image is a virtual upright image. So it says, which point on the graph marks the position of the principal focus? So where the light is refracting outwards on a diverging lens, on a concave lens, that ray actually extrapolate it back when it crosses this line here, which we call the principal axis. It will cross the principal focus of that lens. So it's point B. So which two words describe the image? The image is upright and it's virtual. Calculate the magnification. So I've done it in squares. So I've counted the number of small squares from the principal axis to the top of the object, and from the principal axis to the top of the object. You could have measured it out, but it's easier by counting the squares. So we've got 5 squares is the image height, and the object height was 12 squares, and divide them by each other, we get a magnification of 0.4. So 5 for one mark, 12 for another mark, dividing them up another mark, the answer for the fourth mark. Complete the sentence. As the object moves further away from the lens, the size of the image will decrease. So if this object is moved further and further away from the lens, what will happen to this image? Now, if you think about this ray, what will happen to this ray? If this object was placed here, the parallel ray will still follow that same path and bend outwards, and this dotted line will still stay in the same place. However, when this object is placed, let's say here, this line will come and cross the center point at a shallower angle. So if you just think the ray started here, and it was going towards the center, just like this one here. So it starts off here. So let's say we place the object somewhere here. Okay. And we have got this ray that was supposed to go through the center. Now look at it. How is it going through the center of the lens? This is going to stay the same. So the way that it bends out is exactly the same. So now what we've got is this is the intersection point, and this is your size of your image. So we can clearly see that the image height is smaller afterwards when the object is moved further away. So question 3, you got a light bulb placed quite far from the lens, and then it's moved closer and closer and closer up until it's very close to the lens. Now the light bulb is giving off light, so we're not counting on light bouncing off, but it's got its own light source. So that light source is going to pass through the lens, and we're going to get an image on this side, or a virtual image on this side. Now, when the object is quite far away, we get a real image on this side. When the object is, let's say, that's the principal focus. There's another point when we were drawing ray diagrams. That's twice the principal focus, and that's the principal focus. Now, this object is clearly beyond 2 focal points, and when we drew our ray diagram for an object beyond 2 focal points, we found that the image on this side was a diminished, inverted real image. When the object was somewhere in between the two focal lengths and 1 focal length, we found that the image on this side is still inverted. It was still real, but it was enlarged, so it was much bigger, like a projector screen. And when this light bulb, let's say in this position now, in position N, so beyond the principal focus, what we get is a virtual image on this side. Okay, so we get a virtual image on this side. It is upright and it is magnified. It's much bigger than the original image, and that's how a magnifying glass works. So I've written all that out. So when from this position to before the principal focus, so from there to there, the bulb will produce a real image on this side and an inverted image. And that's regardless whether it's from here to here or from anywhere in between as well. At the principal focus, no image is formed. So if the bulb is placed exactly there, no image is formed. From the principal focus, so when the bulb is moved from there to, let's say, here, a virtual enlarged image is produced on this side, and it's upright, facing the same way. So here I've said that from M to this point, what we get is a diminished image. From this point towards the focal point to 1 focal point, we get an enlarged image. And I had to write that separately because the size of the image differs from diminished to enlarged. So how do we pick up the mark? So we get 1 mark for this section here, 2 marks for actually, so it's a real and an inverted image when the object is from here to here. At the principal focus, no image is produced. That's another possible mark. So we got 3 there. From the principal focus to point N, it's a virtual image. That's your 4th mark. Enlarged upright, that's 5th, 6th. Could have added this final point as a 7th or 8th. So there's so many different marks that you could have picked up. Any one of those would have gained 1 mark each. So here we have a ray diagram that we need to complete. So when drawing out the light that hits the object, parallel bends towards the focal point, object going straight through the center of the lens continues to go through without any refraction. Light is not converging on this side, so it must converge on the other side. It in reality doesn't, but it appears to converge on this side, which is why we get an upright, virtual, enlarged image. Now I am 2 squares out, so plus or minus 3 squares is absolutely fine. So if you've got 10, 20, 30 squares to the image, that's the what the examiner's got. But if you've got like something like me, that 32, 33 tiny squares from the principal axis to where the rays cross, then that's absolutely fine as well. So those are your marks. 1 mark for this line here, 1 mark, so you got a possible 3 marks, 1 mark for this line here, 1 mark for these 2 extrapolating backwards, and you could also pick up 1 mark for this point here. So there's 4 possible marks that you can pick up. So here we've got a question, and I've annotated the question slightly. So when the object distance is 4 centimeters, the image distance for lens A is longer than for lens B. So when the object, so I've drawn a line. So when the object distance is 4 centimeters, the image distance for one of the lenses is around about 6.5 centimeters. The image distance for the second lens is 20 centimeters. So what does that look like in terms of pictures? So we've got a lens here. You've got your object. This is for lens A. So that's lens A, that's lens B. I'll talk about the shapes in a moment. So they're both convex. So the objects are placed the same distance from each type of lens, but the image which is produced for lens A is a lot further away. So this is the image compared to lens B, where the image here is much closer. So